Shoukat, and I'm going to be introducing our project and our team to you. First, we have Faizul, who works as our technical manager, Sun O, who is our lead programming and technical lead, and Fady Rizk, who is our testing manager and also audiovisual lead, and I play the role of project manager. The title of our project is Software-Defined Radio FM Broadcast Station and Receiver. All right, so nowadays everyone is constantly wirelessly connected through some means or another, whether you're texting your friends about what you're going to be doing later this evening or inputting a location into a GPS device. We're very device dependent. The thing is, a lot of these devices are hardware based, which leads to some issues because there can be component failures, and there's also limiting operating conditions. You can't operate hardware if it's too hot or too cold. Whereas with software, you don't have these issues. So basically, we want to minimize the hardware. We want to turn all of that into just one small board and do most of the stuff with software. Turning hardware problems into software problems. The advantage to software is that there's reconfiguration. It's very easy to reconfigure. You can implement algorithms depending on location, time of day, whatever you need. You can tailor it to your needs and have an extremely efficient process. Also, upgrades. Whenever an upgrade is available, you can just download it and you are ready to go. In terms of cost, software also tends to be cheaper because you can write your own or just get it for free a lot of the times offline. Our take on this idea is that we want to turn the process of FM signal manipulation into a software-based one. Other than just transmitting and receiving, our main feature is that we want to be able to transmit multiple signals to multiple stations simultaneously. We have titled our project and this accomplishing these tasks CYRO, and now Spies will go into what we needed to do to accomplish this.
Thanks, Kellie. At the heart of our project is the GMU radio software package. It requires a PC with Linux operating system. The hardware system that we needed was this called Universal Software Radio Peripheral. GMU is a software development kit that was invented in the 1980s. Basically, with it, we can use software to do the digital modulation schemes that are currently done in hardware. The application is actually written in Python language, and the processing blocks are written in C++. Conceptually, you can think of the processing blocks as the replacement for hardware. This is our hardware that we needed. It is called USRP. It's an extremely friendly USB device. It has ARC front ends, which is the dot ports. It can translate frequencies appearing at high range at the input and translate into a lower range at the output. For example, something that's appearing at the 90 to 100 megahertz range can appear at 0 to 10 megahertz range. It has 4 high-speed digital to analog converters and analog to digital converters, which contain sampling rate and dynamic range. The heart of the USRP is the FPGA. It's a Cyclone Alpha Series Cyclone FPGA, which has decimation, mixing, and interpolation capabilities. The Cypress FX2 interface connects the FPGA to the USB, which is connected to the PC. We have the motherboard. These are the 2 daughter boards that we used, and this is the antenna. This top little diagram of our project, basically we have the antenna which sits on the transmission and the receiving boards, which sits on the USRP, which is connected the computer to the USB. This top little diagram of the transmission. 2 channels are coming in from the sound card, which is pre-emphasized to improve the high-end frequencies, which is then encoded, passed on to the modulator. And then this output is passed into the RF transmitter to the antenna and into radio waves. This is a receiving block diagram. We receive radio waves through the antenna, which is passed on to the RF receiver, which is then demodulated, decoded, and de-emphasized, and passed into the sound card from left and right channels. Now, Sun will explain the details.
Thank you, Faiz. Now, I will be describing how we implemented the transmitter, receiver, and multi-station transmitter in GMU radio. So this is a detailed diagram of our FM transmitter. So first thing we did was we opened our music file, which has two channels, left and right. And we add these two channels together and we pass it through a low-pass filter, which just contains information for the mono audio. And then we subtract these two channels and we multiply it by a 38 kilohertz sine wave, and we pass it through a bandpass filter, which contains data for the stereo audio. And there's a 19 kilohertz sine wave, which is a pilot tone or the stereo indicator. And we add these three signals together and we pass it through a pre-emphasis with the frequency modulation on it, and we transmit it to the USRP. And this is our FM spectrum on the transmitter side. So you can see the mono stereo, see the pilot tone, and then the stereo audio. And this is our FM modulated signal. And now I'm describing how we implemented the receiver. So first thing we do is we receive the FM signal on the USRP and we demodulate it, and then the output from the demodulation will be processed through three different filters. First, it will be processed through a narrowband filter, which just detects the pilot tone. If it has pilot tone, it will indicate that the received signal has stereo audio. And the second filter is the low-pass filter, which just extracts data from the mono audio. And third filter is the bandpass filter, which just extracts data from the stereo audio. And then the output from both filters will be de-emphasized and will be sent to the sound. And this is our FM spectrum on the receiver side. So you can see the